Swayam Prabha. Digital India. Educated India.
Hello all, welcome to the lecture 2 of this course. In the last class, we discussed basics about the aircraft. What is the altitude at which aircraft fly? How does it fly? What are the various forces? And then we discussed about the airfoil nomenclature, different series of airfoils. Alright. Now, today we'll discuss, before we deep dive into flight mechanics, let us talk a little bit about history of our aircraft aviation history. Okay. So, the modern aircraft that you are able to see today, that is because of the only one person, that is George Cayley. Okay, so let me write down the name so that it is crystal clear to you. George Cayley. Cayley. So, George Cayley said in 1799 that lift in 1799, George Cayley mentioned that the lift can or the upward force can be created on a curved surface rather than a flat surface. Alright. In 1799, he mentioned this. But before 1799, there were many aviation enthusiasts. There were those who were trying to, attain or mimic the bird flight. But they could not. One name that immediately comes to mind is actually Leonardo da Vinci. Alright, so I'm sure you must have heard about his name, Leonardo da Vinci. So in 15th century, Leonardo da Vinci and aviation enthusiasts, they designed different flapping wing aircraft, what we actually call it as ornithopter. Okay, so let me just write down here, ornithopter. So they tried developing the flying wings. They tried to mimic the bird flight by creating a flapping wing, ornithopters. However, till 1799, George Cayley was solely responsible of directing people's minds from the flapping wing mechanism. Alright, what was the basic flaw in ornithopters or flapping wing mechanisms? Yes. The basic flaw was they assumed that the flapping wings will produce both the upward force, lift, and it will create or it will propel the aircraft forward. That was the basic flaw. And George Cayley was single-handedly responsible for directing people's mind away from this principle. Alright? So, the modern aviation aircraft that we are able to see today, the fixed-wing aircraft, so he is considered the father of the modern aviation today. And he is designated as Sir George Cayley. Alright. So let me just write down few points related to George Cayley. So George Cayley was responsible or I can directly mention here proposed and demonstrated that lift can be obtained or the upward force. We still haven't defined the lift as of now, but we will do that today. Alright, so please bear with me. So George Cayley proposed and demonstrated that lift can be obtained from fixed straight wings inclined to the airstream. Alright, so remember this point, it is inclined to the airstream. While propulsion can be provided by some independent mechanism, such as engine, aircraft engine, whether it is a piston propeller or a jet engine. Hence, Sir George Cayley is called the parent of modern aviation. Alright, so just imagine for the almost 100 or 150 years, humans have tried to imitate bird. So the basic flaw was they assumed that flapping wings will be able to produce both lift as well as the forward thrust, which was obviously wrong. And even there are multiple videos available in the internet related to early flight failures. So I recommend you to watch few videos, early flight failures in the internet related to this content. Alright. Now this, after we realized that we have to have lift separately as well as the forward force thrust separately, and then came the Wright brothers. Alright. So in Wright brothers in 1903, they demonstrated it with experimental result. Okay. So this was put forward by Wright brothers. Let me write down here. Wright brothers in 1903. They demonstrated in 1903 that we know today. Alright. So now I have been talking about the aerodynamic force in the previous class, right? Now from where does this aerodynamic force has started? Alright, we need to know the source of this aerodynamic force. Okay, so there are basically two sources from which this has emerged. One is the pressure distribution and the second is the shear stress distribution. Alright, so let me just write down here. One is the pressure distribution over the surface. The second is shear stress, which is nothing but friction. On the surface. Let me draw the figure of the cambered airfoil over here. Alright. Now this is the pressure which is actually acting on the surface. Pressure distribution of the surface, that be denoted by capital or small p. And similarly, there are shear stress distributions. So this is how the shear stress is actually acting over the body. Now, seeing this figure, you must have noticed this pressure P is actually acting perpendicular to the surface and the shear stress is acting tangentially to the surface. Alright, shear stress is always because of the friction on the surface. Alright, and pressure distribution we have talked at length in the previous class. Alright, so let me just write down the definitions of these two. And one more thing, that pressure and shear stress, they both varies with the location. Alright, if you see here carefully, here pressure will be different, here pressure will be different, here will be different, and so on and so forth. So these both are the point property. Okay, so always remember this. These both are the point property. Alright, now let me just write down the definitions. So the pressure always acts normal to the surface as shown by the directions. So the net imbalance of the varying pressure distributions, I assume you are writing the notes with me. The net imbalance of, or you can write unbalance of, varying pressure distribution over surface creates what we call it as aerodynamic force. Alright, creates aerodynamic force that we thought about, or we were talking about in the last class. Aerodynamic force was lift and drag. We'll come to that in a minute. And the second is the shear stress. Tau, this is because of, is due to the frictional effect. Alright, always remember the shear stress is because of the frictional effect of flow rubbing against the surface. And it always acts tangential to the surface. So please remember this point, it always acts tangentially to the surface. And again, the net unbalance of the shear stress distributions over the surface will create an aerodynamic force. Alright, okay. Now, please remember, it does not matter what is the shape, what is the size of the body, however complex the body shape or the flow is. Nature always has one way of telling us that there are only two forces which are acting over the body. One is the pressure force distribution and the other is shear stress distribution. Alright, please remember, there are only two ways of writing this, that is way of nature of telling us that one is the pressure force distribution, another is shear force distribution. Alright, please do not forget it. The aerodynamic force is created because of the net imbalance of these two forces. Alright, now let me just draw a figure of the airfoil which is at a certain angle of attack so that it is more clear to you. So I am writing here free stream velocity V infinity. Now what is free stream velocity, that I will explain in a minute. As of now, we talked about the angle of attack. Angle of attack is the angle between the chord line and the free stream flow or the relative wind which is coming from this direction. Alright, now let us assume the aerodynamic force is acting at this point. Now what is this point, that also we will be discussing in the coming classes. Assume the force that is acting on this airfoil, it is at this point, and that force is represented by capital R. Okay, so this aerodynamic force is shown by vector R. Which we call it as resultant force so this R can be resolved into two components. So one component, now I am resolving this R component with respect to velocity. Alright, it is up to me whether with what you want to resolve it. So I am resolving it with respect to velocity. One is perpendicular to velocity which is in this direction, and one is parallel to velocity, is in this direction. Alright. Now you must have guessed which the one which is acting perpendicular to velocity. This is what? This is actually the lift, and this is the drag which is acting parallel but opposite direction to the velocity. Now, as I said again, it is up to us. Do we want to resolve the resultant vector r with respect to velocity or with respect to chord line? It is easy to represent, and in aerospace terminology, we generally resolve this r component when compared with the velocity with respect to free stream velocity. Alright. Now let me write the definitions of these two. That is lift L. So this was the lift that we were calling it as the upward force as of today, as of now. Now we will be, from this class onwards, we will be denoting the upward force as only the lift. Alright. So with lift, you should get to know that this is the component of aerodynamic force perpendicular to the relative wind. And then what is drag? Component of the aerodynamic force which is parallel to the relative wing. So please remember, there are two forces, aerodynamic forces. One is the lift, one is the drag. Lift is, you define it as, the technical definition is component of the aerodynamic force always perpendicular to the relative wind. Please see here, this is perpendicular to the relative wind. And then drag, component of the aerodynamic force, that is parallel to the relative wind. This is actually parallel to the relative wind, but obviously in the opposite direction. Now I have also denoted here as the free stream wind as V infinity. Why not V? Okay, we, in many textbooks or in the literature, we will always more or less see infinity term over here. So when we write infinity, what do we mean by that? Alright, that is the question that many students ask. So let me write down here V infinity. V infinity, we call it as free stream velocity. Okay. So this is the velocity of fluid. In our case, we will consider it as air. Velocity of air at infinity. Okay, as the word implies, at infinity, that is far away from the object. Far away from the object in its undisturbed state. So why do we consider this? So it helps in distinguishing from the local flow. Alright, it helps in distinguishing from the local flow. Alright, so this is obviously above, far away from the upstream or from the object. And not only velocity, we always more or less denote density as well as rho infinity. Okay, density also we denote it in this fashion only. That is undisturbed density, which is far upstream of the object. Alright. Now, we have defined the two forces, that is lift and drag. Now, apart from these two forces, will there be anything else which will be acting on the airfoil? Okay. Think about it. Will there be anything else acting on the airfoil or the wing apart from the lift and drag? Okay. Yes. So there will be a moment depending upon which airfoil that you have considered. So as of now I am talking about the cambered airfoil. So there will definitely be a moment about the reference point that we consider. Alright. So let me just write a little bit about it. If you consider a cambered airfoil, what happens here is, now let me consider only the pressure forces, not the shear forces. Alright. If I draw a profile of the forces which are acting over the airfoil, alright. Now consider the force acting on the top surface, that is the net force which is acting at point 1, alright, and the net force which is acting at the bottom, this is denoted by F2. Consider this as point 2. Now notice here the upward force is acting at point 1. Similarly, the forces which is again integrated over the bottom surface, it is acting at point 2. So this, won't it create a moment about the point that we will be considering? Yes. So it will be creating a moment about some reference point. Okay. Moment about some reference point as well. Had been these forces acting at one point only, as F1 and F2, so then obviously there will be no moment about that point. Okay. So let me just write down here. So pressure on the top gives rise to F1 in downward direction. Similarly, we have F2 in upward direction. Now if we have, so that means we have total aerodynamic force is F1 plus F2. Okay, F1 plus F2. And by the way, how can we find this point 1? How can we find this point 2? So these points are generally found by calculating the centroid. Okay, by calculating the centroid using integral calculus. So we can actually find out these points 1 and 2. See, the pressure is acting at the bottom surface is different, pressure acting at top surface is different. So this is integrated to find out this point, or we can also find this point by finding the centroid. Okay. So now these 2 points are actually known to us. Now what was the purpose? To create a higher force at the bottom surface of the airfoil. Okay. Now how will this force be created? If we have F2 should be greater than F1. Okay, only then we'll be having the higher pressure at the bottom and a lower pressure at the top. Then we'll be having the upward force which is required to lift the heavy aircraft that we see today. Alright, remember the aircraft weight was around 1 lakh kgs and even the A380 weight was 5 lakhs kg. Alright, so this heavy lifting is basically done because of from the wings itself by creating a higher pressure difference between the lower and the upper surface of the airfoil. Alright. Now since these points are different, so this F1 and F2 will actually create a moment that will rotate the airfoil. Now the moment will depend upon, as I said, depends upon the reference point. You can consider the reference point over here, for example, leading edge. You can consider another point, maybe trailing edge. Alright, so it depends upon us as long as we are considering the moment about that point. Now, but generally speaking, let me draw another figure here, the cambered airfoil. Generally speaking, okay, we consider moment about a quarter chord point. For example, this is C. Consider this as a quarter chord point, C by 4. Alright. Now we have a lift over here. We have drag in this direction. And this is the moment about quarter chord point c by 4. So this is the quarter chord point mc by 4, and this is the velocity, for example, free stream velocity in this direction. Now the point I am trying to make here is, if you consider the point as moment about leading edge, and the moment about, if you consider another point about moment about quarter chord point, that is mc by 4, will that be same? No, obviously no. The reference points are different, the distance is different, so this will not be same. So it depends upon which reference point are you considering. So let me tell you, for subsonic aircraft, generally we consider mc by 4 only. Alright, we consider moment about near the quarter chord point. Alright, now as an aerospace engineer or a flight enthusiast, we need to know how this lift, I am denoting it by lift, L d by d, how these moments L d m, these are varying with angle of attack. Only then we will be able to design a proper airfoil or wing. So we need to know how this lift, drag and moment are varying with angle of attack. Now LDM, they also depend upon certain parameters. So let me write down the certain parameters. For example, it obviously depends upon the free stream velocity, V infinity. It also obviously depends upon the altitude at which it is flying. Okay, the altitude is taken care by the density, rho infinity. Third is obviously the aerodynamic surface. That is capital S. Okay. Fourth is obviously the shape of the airfoil. Whether it is a cambered or a symmetric airfoil. And it also depends upon the friction effects, right? So remember, the friction effects is generally accounted by viscosity coefficient. And viscosity coefficient we denote it by mu infinity, and for mu infinity of the air it is given as 1.789 10 to the power of minus 5. What is the unit of viscosity? It is kilogram per meter second. Alright. What else lift, drag and moment can depend upon? It depends upon the compressibility of the airflow. Right. So if we have a supersonic aircraft, so then it will heavily be depending upon the compressibility effect. The compressibility effect, which is governed by the Mach number. So I am taking another terminology, that is Mach number. Mach number is nothing but velocity of the object by velocity of sound. Okay. So if Mach number is 1, then the aircraft is traveling at the velocity of sound. Velocity of sound is how much? It's around 340 meters per second. Alright. So generally commercial aircraft, they fly less than Mach 1. They fly at around 0.7 or 0.8 Mach. Alright. So remember these definitions. Mach number is velocity of object by velocity of sound. Now since velocity we have already considered in point 1, so we will account this compressibility effects because of the velocity of sound A infinity. Okay, so compressibility effects are taken care by A infinity. Alright. Then obviously next, it depends upon the angle of attack. So this will, lift, drag and moment will vary with respect to angle of attack. Now see here, to get the lift, drag and moment varying with respect to angle of attack, these many parameters it is actually depending upon. It is depending upon velocity, compressibility effect, A is aerodynamic surface area, S then the density. Alright. So if I give you a certain type of airfoil and tell me how these lift, drag and moments are varying with respect to angle of attack in a wind tunnel, then what will you do? You will put that airfoil in the wind tunnel, take one angle of attack and then vary one parameter, for example velocity, and keep other parameters constant. So what you will get? You will get one stack of data. Alright. Next, what will you do? Next, you will change the aerodynamic surface S and then keep the rest of the parameters same, and then you will get another set of data. Alright. Next, what will you do? Next will be the third parameter. You will be varying density, and then you will be getting three sets of data. So likewise, if you modify all these contents or the parameters one by one, and remember this is for at one angle of attack. Alright. So in this way, you will get full 6 stacks of data, which is a huge compilation of data. And then they need to analyze how lift, drag and moments are varying with respect to these parameters. So now, is there a way of simpler way of reducing this effort or reducing this time as well as cost? Yes. So there is a way. So that method is generally known as dimensional analysis. So you need not to conduct this experiment again and again, which will take a lot of time as well as the cost. Okay. So there is a method known as dimensional analysis. Okay. So in dimensional analysis, what we do is, for example, we write here lift is actually a function of V infinity, rho infinity, S, compressibility effects taken by the viscosity, then A infinity, compressibility effects. Similarly, we can write D and M as well. Alright. Now let us first focus on the lift component, that is L equals to, take some constant Z, right here V infinity power A, rho infinity power B, area D. I am not taking area of the power of C because C we already noted as the chord length C. Just to avoid ambiguity, I am writing S to the power of D. Next, A infinity power E and mu infinity power. Okay. So please note that Z, A, B, T, E, F, these all are dimensionless coefficients. Alright. So it is a fact that the dimensions of the left hand side and the dimensions of right hand side must be same. Okay. Hence the name dimensional analysis. So if we equate the components of, write this equation in dimensional parameters form and then equate the exponents from the left hand side to the right hand side, then we can obtain the expressions for A, B and D. So that we'll be doing right now. So let me first of all create a table for which we have these quantities. For example, let me denote it as physical quantity and dimension at the right side. So here we have lift. So what is the lift? This is just actually nothing but the force, right? So what is force? In the unit of force is actually newtons. So newtons is what? Kilogram meters per second square. Remember, in high school physics we have written in these terms of dimensional analysis in mass, length and time. So kilogram is mass, then m is the length and s square, that is time square. Are you getting? Alright. So the first physical quantity is L, the unit is newtons, that is kilogram meters per second square, and dimensions we can write ml by t square. The next is V infinity, meters per second, that is simple L by T. Rho infinity, density is what? Mass upon volume, kilogram per meter cube. So this is m by L cube. Aerodynamic surface area S, that is L square. Speed of sound, again meters per second, L by T. Compressibility effects, this is the viscosity coefficient. This is kilogram per meter second. I have already denoted the unit. So dimensions will be m by LT. Alright. So now we have written all the dimensions here. So now we are ready to proceed further and find out the expressions for A, B, D, E and F. Alright. So let us go ahead. Now let us write the equation again. That is equation number 1. Writing in terms of dimension, equating dimension of LHS and RSS of equation 1. So what do we get here? Equation 1 was this. This is lift. The lift dimension we can written as ml by t square. Let me write here ml by t square. Next is z, that is a constant, v infinity power a. I am just denoting it here as dimensions power a. No need to write z over here since we are equating only the dimensions. Next is density. Density is unit m by l cube power b. Similarly, next is area power d L by T power E. I hope you are making notes with me. Next, M by L T power F. Alright. So now what we'll do is we'll equate the components of each M, L and D from left hand side and right hand side. See here M, here the exponent of M is 1 at left hand side, and here exponent of M at the right hand side is power, this is B plus F. Alright. So when the base is same, then exponents, the powers are added. Right? Remember this? When the base is same, powers are added. So let me write down here for consider mass M. Equating exponents of M. So as I said, exponent of M and the left hand side is 1, and the right hand side is B plus F. So let me write here B equals to 1 minus F. Consider this as equation 2. Now similarly for equating exponents of T, alright. So here we have minus 2, here we have minus A, here minus E, and here minus F. Okay. Let me write here for minus 2, minus A, minus E, minus F. So we can write A equal to 2 minus E minus F. Let us consider this equation 2. Similarly for length L. For length L we have exponent here in the left hand side is 1. Okay. Here we have A, here we have minus 3B, here we have 2D, here we have E, and here we have minus F. Alright, I hope you are getting this. So for L, I am writing here 1 equals to A minus 3B plus 2D plus E minus F. Consider this as equation number 4. So substituting 2 and 3 in 4. Alright, so you get 1 equals to A was 2 minus E minus F, 2 minus E minus F. We have minus 3B, B already found from equation 2. So minus 3B will lead to minus 3 plus 3F, and rest is same, plus 2D plus E minus F. So this minus E and plus E goes, we will write here 1 equals to, so 2 minus 3 is minus 1. F we have 3f minus f, so we have plus 2f, and also we have one more f over here, so we will get plus f plus 2d. Okay, so now we will obtain the expression for d equals to 1 minus f upon 2. Now finally equation 1 becomes L equals to z v infinity power 2 minus e minus f rho infinity power 1 minus f s power 1 minus f upon 2 a infinity power e and mu infinity power f. So let me bring few terms together so that it starts making sense. Rho infinity v infinity square into s. So here whatever the powers are f, I am keeping it as a one term. So rho infinity power is 1, s is power 1. Similarly v infinity square, I have written here rho infinity v square s. Then a infinity, let us write the power of e. Where is e? Here, minus e. So v infinity will go below, and this a infinity is at the top. So a infinity by v infinity is power e. And finally power f. So mu infinity divided by, so here we have the rho is at denominator, s is also a denominator, that too is square root. Alright. Similarly v is at the denominator. Okay. So right here rho infinity, v infinity, and then we have s power 1 by 2. This is power f. Okay. Now see this carefully. What is this? Velocity of the object by velocity of the sound. Yes. So this is the Mach number. Velocity of the object by velocity of the sound. So this we can write it as 1 by m infinity power e. Now look at this equation carefully. What is this? Rho by mu infinity by rho v s. Okay, now let me make it more simpler for you. What is the area dimension? L square, right? Area dimension is L square. So s 1 by 2 will become equals to L. And for the wing, we'll always consider a reference length as c. Okay, chord length. Remember this equation? Rho v d by mu. If I'm not denoting it by infinity, please assume that here we have rho infinity. Remember this equation? Yes, this equation was for Reynolds number. Rho v d by mu. So for here our reference length will be chord length c by mu. Alright. Now what is Reynolds number? Reynolds number is the ratio of inertial forces divided by viscous forces. Alright, and this is always a dimensionless number. Now what are inertial forces? Inertial forces are nothing but forces due to motion of the fluid. Forces due to motion of fluid. And viscous forces, forces due to friction of the fluid. Forces due to friction of the fluid. Alright. So if we have high Reynolds number, that means what? Inertia is dominating. Right? Inertia dominating. So that means what? The flow will be mostly turbulent. For low Reynolds number, obviously viscosity dominates. So here we will be having a laminar flow. Alright. So now coming to here, reference length S is L square. If reference area is L square, then what about S power 1 by 2? That is nothing but you'll get L. Okay. So now Reynolds number you can mention here as rho infinity, V infinity, reference length is C upon nu. Now let me write here finally the equation that we are getting over here. L equals to Z rho P square S 1 upon Mach number power E. So again here rho infinity, V infinity. Please assume we have infinity over here. And this also we are getting 1 upon Reynolds number power F. Alright. Okay. So now let us define a new coefficient. Defining new coefficient. Instead of the magnitude lift, let us define the lift coefficient CL by 2. Let us denote it as by Z and 1 upon Mach number power E 1 upon RE. I'll let you know in a minute why we are doing this. Alright. Let us denote this CL by 2 equals to this constant Z and Mach number and Reynolds number. Now finally we can write L equals to 1 upon 2 rho infinity V infinity square S into CL. Alright, so this is the basic equation in aerospace. You should always remember this. So from this we can write CL equals to L upon half rho V square into S. Alright. This CL is nothing but lift coefficient. It's nothing but dimensionless numbers. Alright. Now what is this half rho V square? Half rho infinity V infinity square. Remember the kinetic energy, half mv square. Similarly for the flow here we generally denote it by half rho V square. So half rho V square here we call it as dynamic pressure. Okay. So now we have introduced the terms in the first class: static pressure, and this is dynamic pressure. This is dynamic pressure, and this is denoted it as by letter Q. Alright. What was static pressure? Static pressure was the pressure that is created because of the collision of the random motion of molecule. Alright. Total pressure was the pressure created when the flow is stopped isentropically to 0. Alright. So total pressure is equals to static pressure plus dynamic pressure. Okay. So dynamic pressure can be mentioned as total pressure minus static pressure. So always remember these basics about the pressure that we are dealing with here. Alright, static pressure, dynamic pressure, and total pressure. So dynamic pressure is denoted by letter Q over here, half rho V square. So finally we can write this equation as CL equals to L upon QS. Okay. And L equals to Q, even you can write here Q infinity S into CL. Okay. So this derivation was for a given airfoil, and we have obtained CL equals to function of only L angle of attack, M infinity, and Reynolds number. Okay, so let us consider this as equation 5, and let us consider this as equation 6. So likewise, you have obtained the expressions for lift coefficient, and similarly you can obtain the expressions for drag coefficient. That will also be same. CD equals to drag upon QS, or drag upon half rho V square into S. Alright. And moment, what about the moments? We thought about of having lift, drag, and moment variation with angle of attack. Yes. The moment we can write here as Cm m upon qs. Now, is this correct? So, my question is this moment upon half rho v square into s correct? No. Why? Because moment is nothing but force into distance. You have to mention here reference length. Alright, so here reference length is nothing but chord. So you'll get here QSC. Please do not forget Cm is given as m by half rho v square s into c. So most of the students will commit mistakes over here by not incorporating the reference length. This is a moment, not a force. Okay. So now the bottom line here is, now we have these two parameters. The CL is depending upon angle of attack, Mach number and Reynolds number. Now what we'll do is, we'll put the airfoil in the wind tunnel, consider alpha equals to, for example, 5 degrees, angle of attack, then vary the Mach number, and then you will get one set of data. Alright. Then next thing, you will keep the Reynolds number. You will keep the Reynolds number changing or constant, or you will keep varying Mach number, and then you will get second set of data. Alright. So the bottom line is, now from the 6 sets of data, now you only have 2 sets of data for one angle of attack. So this is what actually this dimensional analysis has done. Okay, it is having a significance value. Now we are only dependent upon these two parameters, Mach number and Reynolds number. So Mach number and Reynolds number are called as similarity parameters. Alright, these are called as similarity parameters. We started with having 6 sets of data, having at one angle of attack, then we kept other things constant, velocity constant, compressibility effect as constant, and kept varying velocity. We got one data. Similarly, at different area, we got another data. So we had few sets of data, 6 sets of data. Alright. Now with this Mach number and Reynolds number, now we only have 2 sets of data. Alright. So that is the physical significance of this having the 2 parameters of Mach number and Reynolds number. So we only need to ensure that the wind tunnel is able to have, if we can replicate those conditions, the real flight conditions as the aircraft is flying with Mach number and Reynolds number, we will be able to get the same lift coefficient and drag coefficient. Alright, so let me put a little bit more emphasis on this. Consider an aircraft which is flying, for example, consider Boeing 737. So what is the physical significance of dimension analysis that we are trying to explain? Okay, consider Boeing 737 aircraft which is flying at 35,000 feet and Mach number of 0.8. Alright, so what we'll do is, we want to know what is the CL, CD and CM which are acting at this altitude and at this speed. Alright, remember I'm talking about the dimensionless coefficients, not the magnitudes of lift, drag and moment. Alright, so what we'll do is, we'll put the scaled model of Boeing 737 in a wind tunnel and replicate those conditions as in the real aircraft flying at 35,000 feet. Alright, so if we are able to replicate good Reynolds number, good Mach number, then whatever the CL, CD and CM we will obtain in the wind tunnel result, we will get the same CL and CD as if it is flying at 35,000 feet. Alright, so that is what the significance of the dimensional analysis, and this we have been doing in the wind tunnel test for the past 100 plus years. Alright, and remember I'm talking only about the dimensionless coefficients CL, CD and CM, not L, D and M. These are magnitudes. These are magnitude. Alright. So these will be definitely different at that altitude. Okay. But CL, CD and CM will be same at the wind tunnel as well as at 35,000 feet altitude. That is the physical significance of having CL, CD and CM. But one difficulty we generally obtain is most of the wind tunnels, it is difficult to replicate both Reynolds number and Mach number. Alright. So generally what is done is one wind tunnel will be replicating good Reynolds number and another wind tunnel will be replicating good Mach number. So for the most of the aircraft design, multiple wind tunnel tests are done. Multiple wind tunnel tests are conducted to come up with the final aircraft design. Alright. So always remember, it is difficult to replicate both Reynolds number and Mach number in a one single wind tunnel. So we have to conduct multiple wind tunnel tests at different wind tunnels so that we can replicate both Reynolds number and Mach number at actual real flight condition. Okay, so that is the real significance of dimensional analysis. So what we discussed today was, we discussed a little bit about the history, and then we came up with important expressions of CL, CD and CM. Please do not forget this expression. And then we did the dimensional analysis. And Reynolds number and Mach number are the similarity parameters. So with this dimensional analysis, we are able to conduct tests and obtain the results that we are actually getting at 35,000 feet. So this has been actually our driving force for the past 100 years. Even wind tunnel results are even applicable in today's modern aircraft also. Alright. So we'll continue from here in the next class. Thank you.